It's doing well out there in the universe. I'm going to shut down my live stream on my Linux machine so it doesn't kill my Linux machine. Linux machine's been having hard times today. Just generally speaking. So yeah, come on in, friends. Come on in and join the circle. Sort of like a, I mean, we can do it like a virtual campfire, right? A virtual campfire or a virtual, like a lanai, you know, uh, and the sun is setting, sky is clear, so it's going to be a nice star-filled night. And as we talk here, at least at my location, the sun is going down, and it will be relatively dark in the next hour or so. It'll go from sun up uh, quite a ways to at least nautical twilight, right? There's civil twilight, which goes from sunset to 30 minutes after sunset. That's called civil twilight. And then from 30 minutes to 60 minutes after sunset, that's called nautical twilight. And then from 60 minutes to 90 minutes, that's called astronomical twilight. So, uh, and then there's a little bit of a well, in fact, there's a lot. There's a pretty strong dependence on your latitude, So, a better way to sort of think of it is you are in civil twilight when the sun is between 0 degrees and 6 degrees below the horizon. That is civil twilight. So at least my location here, that seems to be about how long those are. But as you change latitude, right, that's going to change, because it's going to change your perception of sort of the dive angle of the sun. I'm at a pretty low latitude, right? I'm at about 32 degrees north. So the sun really does seem to dive pretty steeply. I it'd probably be worth it to work out exactly what that angle is. Um, it's going to depend on the season, and it's going to depend on your latitude. So yeah, but high latitude, right? Either very very north or very very south. It's going to have a really steep angle, so it's going to take longer for the sun to go into its various stages of twilight. Uh, so yeah, very cool, very cool. Hope everybody sort of liked the uh, this new live stream thing. Uh, Jill, how is everything? Catherine 313, hey. Um, cheers. Atawahinta is in the house. Nice to see you there in the chat. Um, yeah. Well, Mercury is over by Venus now as well. So take a look out for Mercury over this next week or so. And yeah, over the course of the first couple hours uh, of darkness, you will be able to see Mercury, Venus, Earth, right? You can see Earth, Mars, Jupiter, and Saturn, all in basically the same couple hours. So it's, that kind of thing is not incredibly rare. It's really no big deal, but it's always a little bit of excitement when that kind of thing happens. So, yeah, yeah. Cheers. Nice to see all the planets in one sky. That's and that does actually mean that those planets are all on that side, right? That side of the sun, and yeah, a little a little imbalance, but yeah, hardly noticeable at all uh, in the scheme of things. So nothing to worry about. Uh, yeah, yeah, it's no big deal. No big deal. But it's very, very cool to see because it doesn't happen very often. I don't know exactly. I don't know exactly. Should we take a look at our position in the solar system? I actually really, really like what what Heavens Above uh, has done. So I'm going to share my screen. I'm going to share my screen, and I'm going to hide that. I'm going to go over here, and I'm going to go. Oh man, what? Oh, I I I got terribly distracted again. Terribly distracted. Where was I going to go? Oh, that's awful. Yeah, I started thinking about something, and it was just gone. Uh, I don't remember. Somebody remind me what I was gonna just just gonna do. Oh, that's really bad. It's completely escaped me. I was gonna show you something. Remind me what I was just talking about. I started thinking about something else, and off it went. It just jumped. Oh well. We we will continue. We will continue. So let's yeah, I don't uh, sorry about that. I just don't remember what that train was. It just completely left. Anyway, seeing all of these, that's what it was. We're gonna go over to Heavens Above. Yeah. Thank you, Atta. Man, I think I'm just getting really old. Just starting to lose it. Now I'm gonna get my smartphone running. Yeah, I'm just getting old. Thanks. That was a extremely obvious example of that. Turning into just an old dude. Solar system chart. So this one is pretty awesome. I like it. It shows the the outer solar system, right, including Pluto. I don't know why they have Pluto in there. It's not a planet. I thought this was planets. Oh, it says solar system. Yeah, it says outer planets. All right. Well, these guys are being rebels and they're calling Pluto a planet. So, all right, you can be a little rebellious. Anyway, so as you can see, um, so then the square, right? They blow that up to show the inner planets. So there's the sun. Here's where Mercury is. Here's where Venus is. Here's Earth. Here's Mars, right? So as we look outward, right? As we look at the sun, okay, to our left, right, to our east is going to be Mercury and Venus. So that means when the sun sets, right, we're going to see Mercury and Venus, and Mercury is about as far away from the sun as it's going to get right now. So, yeah, take a look at that. But as you can see, all these two planets, if we sort of draw a, so say that we draw a line, right, between the Earth and the sun, right? And then a perpendicular line to that perpendicular line sort of defines our side of the sun and the opposite side of the sun. And as you can see, if you drew a perpendicular line there, Mercury and Venus would be on our side of the sun, right? Now, you can also see that Mars is on our side of the sun. In fact, we're very, very near to Mars opposition. That is when Mars is on the opposite side of the sun, right? Where the Earth will be right between Mars and the sun. That's called a um, opposition because it's on the opposite. Mars is on the opposite side of the sun. So when the sun sets, um, uh, Mars will be rising. Okay, more or less. That depends on your latitude as well. So yeah, let me just do one tangent, and that is I've started a new thing. I just it was suggested to me. Well, it was pointed out to me yesterday, and then suggested to me uh, this afternoon here, my time, that maybe this would be a fun thing to do. So what it is, it's the site called Rabbit. It's rabb.it. That is the URL, rabb.it, and they call it Rabbit. And uh, what you can do is you can play um, like videos on various platforms. So you can play videos from YouTube, you can play things from Netflix, you can play things from Amazon, you can play whatever you want. And I guess the idea is that you create these rooms, right? You create a room and then everybody can, come into the room and all watch this video together. And I think that is very, very cool. And so I'm gonna start doing that at least once a week. And so it's going to be every Monday at 0 hours UTC. Every single Monday at 0 hours UTC, I will be on my Rabbit uh, 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 um, room, and I call it the lettuce bin, bowing to Uncle Bill. So I call it the lettuce bin, and we're just gonna watch videos, watch some stuff, and we can chat. And actually, it looks like we can do video and audio um, on top of all of that. So I want to try all that out, see how it works. I think it's very, very cool. And so, yeah, I think, um, as I said, I want to do it every Monday at 0 hours UTC. Okay. And it'll run about an hour, maybe hour and a half, depending on what it is. I'm not going to, I mean, it can't run very much longer than an hour and a half because I have a 2 hour UTC appointment every single day. So it can't really run more than about 90 minutes or so. But yeah, I mean, I've got lots of ideas, and if you have any at all, uh, let me know. If there's some kind of you know uh, video that you think everyone would be interested in watching. Uh, Maybe it's something that you know you don't think anybody else has seen, or they should see, whatever, right? I'm going to stick to things like Cosmos, right? Carl Sagan's Cosmos, and that's actually what I did today at 0 hours UTC, Monday, July 2nd. We watched episode 8 of Cosmos, and it was very, very cool. It was very, very fun. A couple of people came in, and that was very, very cool and very, very fun. So I definitely want to do that more. Um, and yeah, that's absolutely true, Bobby. Uh, I I definitely want to do it at least once a week, but I'd like to do it, maybe a couple of times a week. I mean, I'm usually around at that time. I could make myself uh, be around at that time. So yeah, I think something like that. I might just uh, sort of do unscheduled. Just uh, get yourself over there, right? And you're gonna have to sign up, right? Um, see, think I can do this from here on my Linux machine. Here, keep looking at that. On my Linux machine, I think I can look at my profile. I hope I can look at my profile. We'll get back to the solar system here shortly. I'm. This is kind of an interesting thing that just has sort of come up, and I think it's kind of a cool idea, and I'm happy to host it. I have no problem with that. So here's the link. I'm going to put it in the chat. So you're going to have to sign up, right? You're going to have to do that. Sorry. Um, but once you're in, you can find me at this link, and you just you make some kind of a request, some kind of friend request or follow request, something like that, and then you can set the notifications, right? So you can get a message saying that I'm on, um, and I'll probably tweet the fact that I'm on, something like that. Anyway, so I think it'll be very, very cool. There's a series. Uh, Gilles, I I wonder if you've ever heard of this British show it was done, I think, back in like the 70s, maybe the early 80s. It's called The Secret Life of Machines, and it's these two guys whose I think day jobs are to make like these mechanical props, but what they do in these shows is they take sort of like an everyday object, like like a vacuum cleaner, right? And they show you how it works. They take a vacuum apart and they show you all the parts, and then they show you how all the parts work, and they try to and they're really really awesome. So if you haven't heard of the secret life of machines, check that out. I definitely want to show a few of these uh, or a few of those on the Rabbit uh, channel because those are very very cool. I also want to watch some In Search of um, shows. Those were always incredibly awesome. In Search of, unfortunately, came a little too early for me. I couldn't when when they were on. I was a little too young, and I there was no way that I could grasp what Nimoy was talking about. I had no concept. I remember watching some of those and not understanding a word he was saying. Right, I was just too young. So I definitely want to watch a few of those. I want to watch more Cosmos. I can upload videos that I have uh, onto my YouTube channel, and we can watch them from there. I've got some, I mean, I've got, I think I've got some interesting movies. So yeah, I think there's lots of possibilities there. So as you can see, I'm moderately excited about that. Cheers. So yeah, I'm probably not going to really announce uh, ahead of time when we're going to have a movie type of thing. So you'll just have to hook up with me over there and hit the notification thing, and then you will know. But oh, I can say this much. Okay, I can say this much for sure. For sure, it will be at 0 hours UTC. For sure. Okay, so it may not be every day, right? It will be every week. Mondays at 0 hours UTC for sure, but it may be on other days as well, but at 0 hours UTC. So yeah, very, very cool. Okay, so getting close to the opposition of Mars. Now, you sort of have to project where Earth is and where the sun is, right? The sun's going to be in the center. Earth is going to be about halfway, right? Maybe a little more than halfway to the edge, and at about 5:30 o'clock, right? So somewhere about there, right? So you can see that Jupiter is also to the east of the sun, and Saturn has just gone through opposition itself. So it is now in officially in the evening sky when the sun sets. Now, as you can see, Uranus is on the other side of the sun. Neptune is on our side. Pluto is on our side. So that's very cool. So every single planet except for Uranus is on our side of the sun right now. That's pretty cool. So yeah, Mercury is about as far away from the sun as it can get. So, Atta, I would say go to Stellarium and make sure that the planets are marked and point yourself west, find Venus, and Mercury is going to be, um, you know, somewhere past halfway to the sun. You see? So you sort of have to draw this line, right? And say, okay, we're looking at Venus like this. How far away is it from the sun? It's a little bit more than halfway to Venus. So that's where it's going to be in the sky, right? So you got to look and see where the sun is going to be. Of course, it's going to be below the horizon, so you're not going to be able to see the sun. But you'll have a good idea about where it is, and then go to Venus, and then go halfway in between, and then a little bit towards Venus, and you will see something, and Stellarium will help you um, uh, be able to pick that out. But yeah, you'll want to. You're going to have to see it in civil twilight, civil or maybe astronomical, right? Because I think the furthest Mercury gets, I think the furthest it gets is something like 28 degrees. I'm not quite sure how far away this one is. It's probably less than that, right? It's probably 23 or 25. So you only have about an hour and a half to see this after sunset. So yeah, but yep, you should be able to see. So, as I said, in a couple hours, you'll be able to see Mercury, Venus. You'll be able to look down and see Earth. You see Mars, you see Jupiter, and you see Saturn. And how it's going to be of of in order in the sky from the sun. It's going to be Mercury, Venus, Earth, Jupiter, Mars, and Saturn. Or maybe Saturn and Mars. Saturn and Mars are going to be really close to one another. Really, really close. You can use Stellarium to do that too. You can sort of see how close Mercury or I'm sorry, Mars and Saturn are going to be. In fact, I think I think Heavens Above has a sky chart. So there's Saturn. We need to just change our time. Go another hour, so we'll go 20. We'll get them both up. Okay, so there's Mercury and Venus and Jupiter and Saturn. I don't see Mars yet. We don't have another hour. See if we have another half an hour. 21. Oh, there's Mercury setting. Where's Mars? Where the heck is Mars? 22. There's Mars. Wow, Mars is way over there. I thought it'd be a little bit closer to Saturn. Hmm. Okay. Well, Mars has a little ways to go until it's so yeah, we're not going to be able to see all of them up in the same sky, right? Venus is setting when Mars is rising. So, yeah, not going to be able to see them all in the same sky. But over the course of a couple hours, you'll be able to see them all. So that's very cool. This, of course, is from my approximate latitude, which is, yeah, Sierra Vista is about an hour away from me driving wise. So very cool. Pretty exciting to be able to see all of them in the same practically in the same sky. Yeah, I think that's very awesome. Cheers. All right, so I noticed that I think it was where is it now? Over on the there it is. So billin.net posted this pretty interesting paper about this thing called a dipole drive. And I thought that we would just sort of take a look at that tonight, the paper, see if we can get anything out of this at all. Because I'm I gotta say, I mean, I don't know too much about this. So the dipole drive is a new propulsion system which uses ambient space plasma as propellant, thereby avoiding the need to carry any of its own. The dipole drive remedies two shortcomings of the classic electric sail in that it can generate thrust within planetary magnetospheres, and it can generate thrust in any direction in interplanetary space. In contrast to the single positively charged screen employed by the electric sail, the dipole drive is constructed from two parallel screens, one charged positive, the other negative, creating an electric field between them with no significant field outside. So ambient solar wind protons entering the dipole drive field from the negative screen side are reflected out, with the angle of incidence equaling the angle of reflection, thereby providing lift if the screen is placed at an angle to the plasma wind. If the screen is perpendicular to the solar wind, only drag is generated, but the amount is double that of the electric sail of the same area. To accelerate within the magnetosphere, the positive screen is positioned forward in the direction of the orbital motion. Ions entering are then propelled from the positive to the negative screen and then out beyond, while electrons are reflected. There are thus two exhausts, but because the protons are much more massive than the electrons, the thrust in the ion current is more than 42 times greater than the opposing electron thrust, providing net thrust. To deorbit, the negative screen is positioned forward, turning the screen into an ion reflector. The dipole drive can achieve more than 6, I think that's millinewtons per kilowatt. Ooh, I don't know what a kWe is. I don't know what a kilowatt kWe is. I don't know what units those are. Does anybody know what uh, what a kWe is? This right here. It's a kilowatt something, but I don't know what. This would be like millinewtons, right? 6 millinewtons per something. Don't quite know what that is. Any thoughts on what that is? So this is a propulsion system that requires no onboard propellant. Yeah. So they're just talking about the shortcomings of solar sails, right? Um, they of course depend on sunlight. And as you move away from a star, your amount of sunlight gets less and less and less. So your push is going to be less and less and less. Um, and yeah, you can only your direction of thrust can only lie within 90 degrees of the vector of sunlight. Um, so the amount of thrust can be derived by reflecting light is at best 0.0067 millinewtons per kilowatt, which means that very large sails, which necessarily must have significant mass and be difficult to deploy, must be used to generate appropriate thrust. As a result, while solar sails have been studied since the time of we are only now beginning to experiment with them in space. So there's a magnetic sail, uses a loop of superconducting wire to generate a magnetosphere to deflect the solar wind. Assuming the development of high temperature superconducting wire with the same current density as existing low temperature superconductors, a mag sail should be able to generate significantly higher thrust to weight than is possible with solar sails. However, such wire has not has yet to be developed. So they're stuck there. So electric sail. Yeah, that's kind of interesting that there's a difference between a magnetic sail and an electric sail. I'm gonna have to maybe understand that a little bit better. Oh, it cannot. Neither of them can operate inside a planetary magnetosphere under other than as a drag device, limited to the potential direction of its thrust. Because of the low momentum density of the solar wind, electric sails must be even bigger than solar sails. However, because only sparsely spaced thin wires are needed to create sail area, higher thrust to mass ratios can be achieved. Talking about the EM drive there, which I think has been shown to not be standing up to scrutiny, as I recall. So the principle of operation of the dipole drive while accelerating a spacecraft within a planetary magnetosphere is illustrated in figure 1 below. So sorry, I can't zoom in on this. Here's the plasma wind coming in here like that. And which has protons and electrons. The as these guys move through an electric field, the electrons will be reflected and the protons will be accelerated. So the net thrust, there's going to be so yeah, that's kind of interesting. It's going to the direction of motion is towards the source of the wind. So we see two parallel screens, with the one on the left charged positive and the one on the right charged negative. There is thus an electric field between them and effectively no field outside of them, as on the outside of the field of each screen negates the other. There's also a voltage drop between the two, for which purpose of this example we will take to be 64 volts. Protons entering the field region from the left are accelerated towards the right and then outward through the right-hand screen, after which they escape the field and experience no further force. Protons entering from the right are reflected towards the right. There is thus a net proton current from left to right and a net proton thrust towards the left. In case of electrons, the situation is exactly the opposite, with a net electron current from right to left and a net electron thrust towards the right. Note that while electrons entering from the right will be greatly accelerated by the field, reflected electrons will only be reflected with their initial velocity. There will also be an electron current through the outside plasma to neutralize the net proton flow to the right. Well, they're saying the space plasmas are electrically neutral, which that's don't know about that, but okay. Just catching up on the chat here. Yeah, we're just trying to figure out ways to move around without having to carry all of our fuel. That's a big problem, because we're going to have to either carry it along with us or manufacture it, and both of those things are big problems. So if we can use the material that's in space itself, um, maybe that's enough. So I don't know. Assuming a 500-watt power source to drive the system, the electron current negates about 2% of the thrust produced by the proton current. The maximum possible jet power is thus about 490 watts, watt joules. I think that's watt joules. I don't understand that unit though. Assuming additional inefficiencies, we will round this down to 400 watt joules for a total system electrical to jet power efficiency of 0.8. A coulomb of protons has a mass of 0.011 milligrams. Oh, I didn't know that. If the jet power is 400 watts and the potential difference is 64 volts, so the proton current will be 6.25 amps and have a mass flow of 0.0652 milligrams per second. Relationship to jet power to mass flow and exhaust velocity is given by that. And so, okay, well, this is very cool. It confused me for a second because they're using C, which is a special variable, but they're just using it as a regular old variable, um, using it as exhaust velocity, right? So here's the equation. You you plug it in, you plug everything in. You got to do a little bit of algebra to solve for C, right? You have to divide this by m, multiply this by 2, then take the square root of that whole thing, and you get c. 110,780 meters per second. So thrust is the mass times the velocity. So that's 7.2 millinewtons. So we're seeing, what he's saying is that they're seeing a thrust to power ratio of 14.4 millinewtons per kilowatt something, more than 10 times better than that claim for the EM drive, but then entirely within the known laws of physics. Very cool. Cheers. Cheers to the known laws of physics. Dipole drive can thrust in any direction, raising or lowering its orbit or changing its orbital inclination. In addition, when used as a drag device, the dipole drive can create twice the drag per unit area as the electric sail. Yeah, that was that had me fooled there for a second there, Ata. It's like, why is the speed of light changed its value? So the dipole drive in planetary orbit. Let us therefore analyze the system further. The dipole drive exerts no field outside of its screen, so the only plasma it collects is a result of its own motion through the surrounding medium. So how big does its screen need to be? We consider first the case of the above described dipole drive system operating at LEO at altitude of 400 kilometers, being used to thrust in the direction of orbital motion. It's moving forward at an orbital velocity of 7760 meters per second. The average density of ions at this altitude is about 1 million per cc. Assuming conservatively that all the ions are protons, the required ion mass flow of 0.652 milligrams per second will be swept up by a screen with a radius of 127 meters. So that's pretty big. That's pretty big. I mean, that's definitely not small. It's definitely not huge, right? It's not kilometers in size. It's yeah. So, and that amount of mass will produce a thrust of 7.2 millinewtons, which is 10 times what they're doing now. So that's pretty cool. It may be noted, however, that at 400-kilometer altitude, there's also an oxygen plus. There are also oxygen plus ions, each with a mass 16 times that of a proton, with a numerical density of about 100,000 per cubic centimeter. We therefore more than double the ion mass density provided by the protons alone. If these are taken into account, the required scoop radius would drop to about 80 meters. Go to higher voltage. If you go to higher voltage, you reduce the scoop size. if you quadrupled the voltage to 256 volts, the exhaust velocity would double, right, to 222,000 kilometers per second, allowing us to cut the mass flow by a factor of 4 and the scoop radius by a factor of 2 to just 40 meters. The thrust, therefore, would be cut in half. Thrust would be cut in half, huh? Huh. I wonder why. I don't know. As we go up in altitude, the plasma density decreases, as does the orbital velocity, requiring us to go to larger scoops. Okay. So it may be noted that Mars, Venus, and Jupiter all have ion densities in low orbit comparable to those above. For example, Mars has 500,000 cc at 300 kilometers. Venus has 300,000 cc at 150 kilometers. Jupiter has 100,000 cc at 200 kilometers, making the dipole drive attractive for use around such planets as well. Many of the moons of the outer planets also have ionospheres, and the dipole drive should work very well in such environments. The dipole drive in interplanetary space. So they say that it can also operate in interplanetary space. Um, Compared to planetary orbit, the ion densities are lower, but this is partially compensated for by higher spacecraft velocities relative to the plasma wind. As a result, the required scoop sizes are increased compared to orbital uh, to planetary orbital applications, but not as much as, but not by as much as considerations of ion density alone might imply. I won't get into all of this. So uh, in interplanetary space, you would need a a screen that has a radius of almost 800 meters. So you're talking about 1.6 kilometer diameter uh, screen. That's a mile, right? Is that a mile? Yeah, that's a mile. So that's at doesn't say what voltage. Yeah, it doesn't say what voltage. So using a lower voltage just means that it has to be even bigger, right? 2.2 kilometer diameter. Talking about using a dipole drive on a microsatellite might employ 5 watt dipole drive. That might be enough. Thrust and diameter of dipole drives in interplanetary space, 1 kilowatt something. So they can get them pretty darn small. pretty darn small. The dipole drive can be used to accelerate a spacecraft at velocities greater than that of the solar wind. For example, consider a spacecraft moving away from the sun at a velocity of 1,000 kilometers per second. The solar wind is following it at a velocity of 500 kilometers per second. So relative to the spacecraft, there's a wind moving inwards towards the sun at a velocity of 500 kilometers per second. In this case, to accelerate the spacecraft would direct its positive screen away from the sun. This would cause it to accelerate protons sunward while reflecting electrons outward for a net outward thrust. At 500 kilometers per second, the protons are approaching the spacecraft with a kinetic energy equal to 1,300 volts. Kinetic voltage. Have to think about kinetic voltage. Can't wrap my head around that one. And this is a little complicated too. Sorry that I can't zoom in on these anymore. The solar wind has a density of 6 million protons per cubic meter at 1 AU, with ambient density decreasing to 1 million per cubic meter in interstellar space. If we take the former value, we get a thrust of 2.5 nanonewtons per square meter. Woo! If we take the latter value, it would be 0.42. The proton current at the smaller value would be 80 nanoamps per square meter, which at 3,900 volts works out to be 0.312 milliwatts per square meter. The thrust to power ratio would therefore be 1.35 millinewtons per kilowatt. Okay. So it can get to speeds above 500 kilometers per second, above the solar wind speed by sailing across the wind. As the spacecraft's crosswind speed increases, it becomes advisable to turn the sail to ever greater angles to the solar wind and increasingly normal to the crosswind. Yeah, it's very looks pretty interesting. I definitely like to see some experiments. Definitely like to see some experiments. So let us consider the case of a 2 kilogram microsatellite operating in LEO with 5 watts of available power to drive the dipole drive. If we operate it with a voltage of 16 volts, it'll produce 28.8 uh, millinewtons per kilowatt something, or 0.144 millinewtons of thrust overall. It would have an acceleration of 0.000072 meters per second. Um, this would allow it to generate a delta V of 2,288 meters per second in a year, sufficient to provide extensive station keeping propulsion, substantially change its inclination, or to raise it from a 400-kilometer altitude orbit to a 700-kilometer orbit in 1.6 months. So it would need a scoop of a radius of about 16 meters. And at 700 kilometers, it would need a radius of 58 meters. So again, not that's not really small, but it's not really big either. That's not bad. That's not bad. Each square meter of mesh would thus have about 1 meter length of wire. So a scoop with a radius of 16 meters would have a mass of 32 grams. If the propulsion system were used simply for station keeping, inclination change, or deorbit functions at the 400-kilometer altitude, that's that that's all that would be needed. Then they talk about a bigger one, so I'm not going to get into that. So BillN.net, thank you for the interesting article. It's things that they think they're on to something. I'd like to see them do some experiments. The above examples, we specified aluminum wire with 100 micron diameters. Aluminized spectra. Spectra is some kind of metal of some sort. It's about 100 times the yield strength of aluminum and roughly a third the density. So spectra strands with 100 micron diameters and a coating of 1 micron of aluminum would thus be far superior material for dipole drive systems. So very cool. Here we go. There's a nice picture there. So these small ones they can use to turn and stuff like that. Let's see. Dipole drive is a promising new technological concept that offers unique advantages for space propulsion. Requiring no propellant, it can be used to thrust in any direction and both accelerate and decelerate spacecraft operating within planetary magnetospheres, in planetary space and interstellar space. It can generate both lift and drag, and its maximum velocity is not limited by the speed of the solar wind. I want to see if they're planning anything. Um, Leo, such an approach could potentially reduce the mass of a manned lunar mission to within the launch capacity of a single Falcon Heavy. Because it needs no propellant, the dipole drive offers the unique advantage of being able to provide its propulsion service to any spacecraft indefinitely. While the dipole drive was most attractive in orbital space, whether ambient plasma, uh, where the ambient plasma is thickest, it can be used in interplanetary space and even enable interstellar missions as well. Many technical issues that need to be resolved before practical dipole drive spacecraft can become a reality. However, both the theory of dipole drive operation and its potential benefits are clear. Work should therefore begin to advance it to a flight status. The stars are worth the effort. All right, well, very cool. Atta, take care. Hope you're still there, saying goodbye. All right, yeah, very cool. Thanks for coming in. And yeah, you know what? I think I'm gonna call it too. The um, the comments the comments were pretty interesting. Um, so I don't think that I. Yeah, we've got this. It's over on my Discord server. It brings you right here, and you can look at all the comments. It gets pretty heavy. Quite a few of them. And see, it gets into some mathematics and just all kinds of craziness. So yeah, I don't know what the consensus is on this, um, but it's looks. I mean, it looks pretty interesting. Pretty interesting. So we'll see. We will see. Yeah. All right. I'm gonna get out of here. I'm gonna get out of here for this live stream. So take care, everybody. If you're just coming in, don't know what this is, never seen this craziness before, this is Astronomy Daily Live. This is a live stream done every single day at 2 hours UTC. Now, I say every single day, and it sometimes isn't every single day, but I definitely try, and for the most part, yeah, that's true. So every single day, check in, 2 hours UTC. If I'm not going to be able to make it, I try to let you know one way or another. Um, for instance, this um, July 5th at 2 hours UTC maybe will be canceled. Don't know yet. I will let you know. So July 5th, 2 hours UTC might be canceled, maybe. Depends. Got a music gig earlier in the day. Don't know how long it's going to run. Don't know if I'll be back in time. I should, but I don't know yet. All right. Take care, everybody. I'll see you on the spin. Okay. It's a nice, smooth spin, but it's fast. Fast. All right. Take care, everybody. I will see you in a little less than 23 hours. All right. Take care. Bye.